Okay. Okay. So the main goal for today is going to be talking about Windows exploit mitigations and how they're bypassed, their weaknesses. And the big lab for today will basically be taking our payloads from yesterday, or really just your payloads will have to be modified extensively, so you'll basically redo them from scratch, but kind of customizing a new payload to exploit the same program as we exploited yesterday, just with all mitigations available to us on Windows XP turned on. So it's definitely possible, but it's a lot of work, so it's going to be kind of like a day-long lab there. So that should give you a good idea of how you build these exploits to really work on production systems, because in the real world, when you're trying to write an exploit, you're going to run into some kind of mitigation these days, unless you're trying to exploit Windows 98 or something like that. So you have to build some of these things into your payload, or at least be aware of some of them. At the very least, you'll probably run into safe SEH, maybe or maybe not dev, but I'll get into all that shortly. Okay, I was about to do that. So before we get started with the mitigations, there's a couple other sort of vectors of attack that Windows provides us that I wanted to talk about. And the first is that most applications in userland in Windows are written in C++, and C++ provides us a lot more targets in the standard C language for buffer overflows and things like that. And that's because C++ uses a crazy amount of function pointers to accomplish its classes and inheritance and polymorphism and etc. So whenever you have something in C++, a lot more function pointers are flying around and would be the case if you're just programming in C. So those are just more things that provide you an opportunity to overwrite to gain control of EIP. Okay, so like in this case, you don't really need to know C++. C++ is just doing basic C++ polymorphism, where you have a person class and a student class, and whoever's a student is also a person. And in C++, it sort of dynamically decides, which action function to call, depending on if you're referencing this particular class as a student or as a person. And the way that all works is by using these crazy amounts of function pointers. And I'll actually show that to you in a debugger. So yeah, let me actually just get into a debugger and show that. So you guys can follow along if you want, but you don't have to. I'm not going to be asking you to do anything with this lab. I just want to show you what's going on here. Okay, so here's some typical C++ classes, same kind of code I just showed you on that slide, and I just sort of packed in like a buffer overflow in here into one of the methods. And what's going to happen is this is actually going to override what's known as the V table for the C++ class, and that V table stores a bunch of these function pointers, and the V table is basically storing a function pointer for each one of these methods implemented by the class. And when you smash that, whenever one of these methods is called, you're going to get an access violation, obviously, since all those pointers will have been corrupted. Like a win main or something. Yeah, so access violation probably because I'm just trying to. So let me try to show you the disassembly actually. So whenever you see like a C++, class is corrupted, let me change the font. You're going to see some code like this. And you'll see this type of a code construct appear in a lot of vulnerability reports. So if you're just to look at the EIP that the function was crashing on, it doesn't look very interesting. It's just move EAX, EDX. And but then the next line is call EAX. So what's happening here is it's doing some like digging down in a pointer table to figure out what function. In this case, we've actually sort of the pointer to the V table. So notice we can control wherever the V table is pointing, and so this would obviously be exploitable. Since we can make EDX point like the stack, and make the stack contain some function pointers to our code, and that would end up calling our shell code. So you see this thing a lot in like use after free conditions when they're exploitable, and I'll sort of draw that on the board and explain what's going on there. But I want to actually show you in the debugger what these C++ classes look like. So, where are my symbols at? So yeah, whenever you see EIP equals 414141, that's a good sign that, you know, good things happen for an attacker. Okay, so it's not hitting the main breakpoint for some reason, but I can actually look backwards on the stack to sort of show you what the C++ class is supposed to look like. The main thing I was trying to demonstrate was that whenever you declare a class in C++ with a call to something like person P1 or student P2, what actually exists on that stack location is a pointer to this table of function pointers. So whenever you declare a class like that, you're basically putting something on the stack, which is a pointer to a bunch of function pointers that will be used. So that's just one more target that you have for trying to override to gain control of EIP. So in this case, if we just do a little reversing and looking up the disassembly, we can see that, all right, EDX is bad. Where's EDX coming from? EDX is coming from EAX. EAX is coming from EBP minus A4. So A4 is where that class supposedly exists on the stack. So if you look at that EBP, it's like a pointer to something. And I guess all this has been completely trashed. But the debugger doesn't want to play nice today, but I just want to show you guys that keep in mind whenever you see one of these classes declared in C++, that's just like another target for you to override. You can override one of these things, and it's implementing these polymorphic methods using function pointers to accomplish that, so that's one more target you can exploit. Now, C++ isn't all good, though, because it can actually make static analysis very hard. And the reason why C++ also implements a lot of this stuff through things like call-through registers. You can see call EAX, and this kind of thing happens a lot. And that makes it hard for tools like IDA-Pro and so forth to know, where the control flow is actually going, since the control flow is kind of dynamically decided at runtime. So this can make static analysis quite a bit more painful. You'd actually just have to set a breakpoint here and see where the program is actually going during the execution. Okay, yeah, luckily I had my debugger working properly. This was just showing you DC P1. P1 is one of those classes that I declared. the first thing that P1 is actually pointing to is that 415760, and that should be a pointer to a bunch of other function pointers. And at first, you can see I got that 415760 value. I guess it was just the very first one here, first thing that the P1 class is pointing to. And then pointing at that 415760s are actually a table of function pointers that implement all of our class methods. And the first one is the action method or whatever. So function pointer is good, more stuff to overwrite. And then if you were to actually play around with that project file in there, you can see that it's pretty easy to gain control of the EIP of the event there. EIP equals 41414141. It's always what you want to see. Okay, so before I start on exploit mitigations, I want to talk about use after free a little bit because it's been a vulnerability that's been kind of real popular since 2009 with web browser exploits in particular. You see it coming up a lot. And it's sometimes not so clear what use after free is or why it's an exploitable condition. So I want to reason about that over here on the whiteboard a little bit. So Bill, if I could get the camera on the board. So what use after free is exploiting is actually what we call dangling pointers, which is, pointers in C or C++, not type-safe languages that point to a freed memory, kind of like released memory. So, I'm trying to figure out the best way I can draw this so you guys can see. All right, so in C++, we usually do something like, person P equals new person. And what this does is it creates a pointer P, which points to somewhere on the heap. This is my heap right here. Remember, heap grows up. And somewhere on the heap is the actual V table for P, because that's what P is actually referencing. It's V table. And what happens is, if we were to free P, or I guess delete is the actual C++ lingo, but I'll just say free to make it more clear. Then the keep allocator marks this memory right here as available. So another allocation can come up and take this memory away. If the heap allocator wants to say, all right, I want to reissue this because it's been freed, so it's available. But the problem here is I have a dangling pointer. Because P still exists, but it points to freed memory. So how use after free is exploited is in the browser you do some crazy document class syntax to generate one of these dangling pointers. And then you trick the browser into using that dangling pointer. Normally, IE should keep track, Internet Explorer should keep track of the fact that P has been freed and it's no longer valid. But under certain vulnerable conditions, you can force it to reuse P after it has already been freed. What typically happens is, all right, so free has been P'd, you accomplish some JavaScript syntax or something like that, some type of vulnerability. And then you force Internet Explorer to do an operation like P, action. And what has typically happened in this case, the allocator has already come out and reissued this memory to JavaScript requested some more memory for its strings. So this now points to hello or some other document class stuff or whatever. So this has been reissued. And so when it goes to P, try to do P action, it assumes this is like a V table, a pointer to a virtual table. And now it's obviously been overrun with this JavaScript data. And then bam, it's a crash, like a bad pointer dereference or whatever. So It's not immediately clear why this would be exploitable, but once keep spraying comes into the arena, that's where it becomes really easy to exploit these things. So what the attacker actually does in like a use after free exploit in a browser is in between forcing the browser to use the dangling pointer and actually creating the dangling pointer, in between this time frame, they do a keep spray. And what a heap spray does is it uses JavaScript strings to allocate like giant amounts of memory that's equal to your shellcode. And so it's just forcing the heap to be full of your shellcode. So P now points into here, which is available. The heap spray comes and allocates this as equal to your shellcode, this is equal to your shellcode, this, all by creating JavaScript strings, because the JavaScript string allocator and the Internet Explorer process share the same heap pool. It's kind of the reason why these can be exploited. So all this is now equal to your shellcode. And look, this available spot is now equal to shellcode. And then when it goes to use the C++ class again, when you trick the Internet Explorer engine into doing that, it's actually going to execute your shellcode. And that's how these use after frees are exploited. So it's really easy in a client-side scenario when you can keep spray and assure that you can overwrite where this dangling pointer is pointing to with attacker-controlled data. Where it gets really complicated is when you're trying to exploit a server-side vulnerability, because you have to get the allocator to somehow reissue this chunk of memory to you in a way that you can control it. That way you can control what the dangling pointer is pointing to. Very easy with the browser exploit because you can just heap spray and force the entire heap to be equal to your shellcode. Very complicated in like a remote server-side exploitation scenario. Generally it involves making like thousands of connections to the vulnerable server. That way the heap is still filled up with like attacker-controlled data, and you can get that dangling pointer pointing to attacker-controlled data. So that's a very popular bug that's been around since, or started to be exploited, I guess, really since the Aurora vulnerability came out. And heap spraying makes it super easy to exploit this. The second you find it, do a heap spray, and it's kind of like automatic exploitation. And you can see it's, or if you've done any type of C++ programming, it's easy to reason about why these would be difficult to detect. And whenever you have a like a global variable or a class like that, a lot of times you have like 10 different references to it. So 10 different pointers to the same chunk of memory that's been allocated. If any one of those pointers gets freed, the rest of those pointers are now invalid. They're dangling. So if any one of those 10 pointers gets freed, then the rest are bad, and keep tracking of, okay, this one's been freed, so I now have to nullify the rest of them. It's pretty hairy. I think Microsoft theoretically has some crazy like dynamic binary instrumentation engines that are just like automatically detect these scenarios, but obviously they're still coming out. So you can't rely on a computer to find them all. Like I think one of the more recent ones was a use after free scenario in the Microsoft XML core library that they recently had an exploit for like a week ago or so. That was kind of like the same deal. Okay, so that's what we're dealing with in Windows as far as exploitation generally. We got general stack overflows, exception handler overrides, C++ vtable corruption, use after free scenarios. And that's going to hit like 95% of the vulnerabilities we see in Windows. You also have heap overflows and things of that nature, but I'll just say that heap overflows are very complicated in Windows, XP, and beyond because Microsoft is trying to harden their heap allocators so that overriding heap meta information, you get that arbitrary 4-byte overwrite that we had with Corey's crappy allocator, becomes much more difficult. It's still possible to trick the allocator to doing an arbitrary 4-byte overwrite, but it involves substantial massaging of the Windows heap to get it in the right layout for that to be possible. And the Windows heap allocator is extremely complicated, so getting everything in the right order is quite difficult. So what you generally try to do in a heap overflow situation is not even mess with trying to overflow the meta information. They keep the chunk control block information because it's just too complicated, too hard to try to manipulate. Instead, you just try to overwrite a C++ vtable class or another function pointer that's stored somewhere else on the heap that you're overflowing. So instead of trying to attack the heap allocator, you're really trying to attack application data that's stored on the heap that you can overwrite with your heap overflow. Generally what you try to do. Okay, so before I move on to exploit mitigations, does anyone have any questions about those sort of general attack vectors I just discussed? Anyone have any questions about the exception handler overrides? Okay. So let's get on to these exploit mitigations. Like I mentioned before, whenever we're writing real exploits for Windows, at least some of these will come into play. In Windows XP, we have to worry about all of these, really, except for ASLR. Windows XP does not have ASLR supported by Microsoft. I think there might be some custom third-party solutions out there for implementations of ASLR, but by default, even with the enhanced mitigation framework or whatever, no ASLR. Okay, so it's a common held misconception that exploit mitigations have rendered vulnerabilities unexploitable, or that they've made most of them unexploitable. The fact of the matter is most vulnerabilities, the majority of them, are still exploitable. They just require a lot more work for us as the exploit developer to pull it off. There's no more simply pointing the return address of the stack and then returning to our shellcode. We have to do a lot more magic to get our shellcode to execute. But whenever you have your friends tell you, oh, exploits, why are you studying that? Those have been rendered obsolete by ASLR and dev. You can laugh in their face because they're totally wrong. Okay, so there's kind of two classes of exploit mitigations. Mitigations that are applied on like a per process, per binary basis, and those that are applied on a system-wide basis. So things like def and, or actually just kind of. So GS protection is definitely a per process mitigation. It's something you have to tell the compiler, I want this binary to be produced with GS protection. It's actually putting extra code into your binary to try to protect it. And I already showed you guys this yesterday. And so like in this case, this is basically what I showed you yesterday. I do a buffer overflow. I try to change the return address. When all this finishes executing, I should theoretically have control of EIP. And then instead of my return address being used, the process just terminates immediately. The return address is never used at all. And that's basically GS protection saving us. And so what this GS protection is actually doing is if you were to put one of these Visual Studio compiled binaries into WinDebug and look at its function prolog and epilogue, you would see additional code inserted in there. In the beginning, you'll see something like this: move EAX, dword pointer security cookie, something like that. And then it pointing stick. So essentially what it's doing is it has some random value that's generated. It makes it more random by XORing EBP, which is, I don't know, I guess supposed to add more entropy. And then it saves it basically in between your local variables and the return address it's saved. And then right before the function returns, right before it even tries to use its return instruction, it's calling a function which is basically making sure that security, like randomly generated security token, is still intact. So if you were to smash the stack, you would overwrite the security cookie, and then when it went to return, it would call this first, see that the cookie's been corrupted, and it just does like an exit process immediately.
Where are those stored? Cookie?
What was that?
Cookies stored on the stack?
The cookie is on the stack, yeah, but you don't know what it is, so you can't reproduce it. It's the theory. because it's sort of random in nature. Now there are some cases where you'll see like static cookies, and if it was static, you could just obviously reproduce the value. What you see in Linux is that instead of like a randomly generated cookie, they make the cookie contain a lot of bad bytes, like null bytes, new line characters and stuff like that. Bytes that are generally hard to produce as an attacker and like a string copy, ASCII string type overflow. So instead of trying to make it random, they just try to make it hard to reproduce. Two different schools of thought there, because if you had some type of information leak bug that allowed you to look at the contents of the stack, which actually isn't that rare, then you could obviously just see what the value of the cookie is and then reproduce it in your overflow, and then the corrupted return address would be used. But even if you knew what it was, but it contained bad bytes, like null bytes, you couldn't reproduce. But it turns out this is like the weakest form of exploit mitigation, kind of like the easiest one to bypass. And without you even realizing it, you basically bypassed it yesterday. Even if GS protection had been turned on, your safe exception handler payload still would have worked. And that's because you would have gained control of EIP before any of this stuff ever executed. Because you generated an exception before this executed. You had already corrupted the exception handler at that point, so you gained control of EIP way before any of this stuff would have been happening. Another thing about GS protection before we move on is that this adds a lot of overhead to functions. So you can imagine if you have a very small function like one that just checks, is global variable true? Is this true? Return or something like that. Just a few assembly instructions. You would be making it like 300% slower by adding in all this extra security code. So Visual Studio actually applies some heuristics and tries to decide which functions it should apply this GS protection to and which ones it should not. And the rules are kind of weird and hard to understand. Like, if your function contains an ASCII string more than 4 bytes, then it will apply this security protection. If it does not contain an ASCII string, then it won't apply the security protection. So if you have instead an array of integers, instead of like an array of chars, it won't apply this. But you can still have an overflow in the integers. It's still the same effectively, and then you wouldn't have had any GS protection. So I guess they're just trying to be smart about where they're applying the security check by default, so they don't make all of their binaries produce a lot slower. Okay. Oh, I dropped it. So depth, this is something we talked about in Windows, in Exploits 1, excuse me. And in Exploits 1, we called this no execute stack, which was basically the first evolution of depth. So back in the day, the general MO for exploits was you point the return address at the stack at a data region that you can put your data in, and then you get control. Your shellcode is executing, well, that's great. And then the obvious thing that was being abused here was executing a data region as code. And so these Linux kernel guys were like, well, obviously the stack is data and EIP should never be pointing there. And so this guy, Solar Designer, came along and made a patch for the Linux kernel that made it so that it would check if EIP was pointing at something marked as data or something marked as code. And if EIP was pointing at something marked as data, it would kill the process essentially. But there wasn't any hardware support for it to begin with, so it was basically like a really brutal hack to accomplish this, like screwing with the page fault handler and so forth. So it was never really widely adopted by the Linux kernel since it was so kind of hacky and not very, stable. But these days we have hardware support for depth, so the processor can actually mark its page tables as this page is executable and this page is not executable. And then the processor's constantly checking, is EIP, is the page it's about to point to marked executable or not? And if it's not, then it, alerts the OS or whatever. So, by default, all these data regions that we have overflows in, like the heap, the stack, and so forth, are going to be marked not executable. So we can't just automatically put our shellcode on the stack and then return to it. Windows will stop the process and give you a nasty dep policy violation script. So here's an example. I think this code actually exists somewhere in the class directory. It's just I'm declaring like the calc shell code, then I make a function pointer to it, and then try to execute the function pointer. And all of this is stored obviously in a data region. It's just like a global data region. And without dep, whatever, that's totally legit function pointer pointing to the shell code. And then with dep, if you tried to do this, it would just crash, basically, because EIP is pointing in a data region, no good. Windows says, I don't think so, dog, I'm going to kill you. And then these are the default dep options we use here at the company. And the way this works is you have several different options for how dep is supposed to operate. You can have dep completely off, nothing uses dep. You can have dep completely on, every process has to use dep. Then you have two intermediate modes, which is typically what is used. You have opt-in and opt-out. Opt-out, which is what we use by default. This is what the dep enabled line looks like on your virtual machine. Opt-out means that every process has dep enforced on it unless the process explicitly says in the binary, and it's like PE header, I am not compatible with dep. You can set a flag, the bit in the PE header that's going to say, this process is not compatible with dep, so do not apply dep to me. And in the opt-out mode, if EIT was ever pointing at a data page, the process shepherd in Windows would say basically, okay, EIP is pointing at a data region, but this thing is marked as not compatible with dep, so I'm just going to allow it. And turns out that a lot of executables do opt out of dep, like applications and so forth. All Windows binaries that Windows ships do by default do opt into dep because they opt into all their exploit mitigations in general, but a lot of applications don't opt into this for whatever reason. And then the other option, intermediate option, is opt-in, where basically dep will be turned off for everything except binaries that explicitly say I want to be like want to have dep turned on for me.
I do actually have a question.
You guys have any questions about GS or dep so
I
far?
always think of dep as basically just a marketing term that Microsoft uses for non-executable stack, but really at some point I looked it up and they say that dep is subdivided into hardware dep, which is the use of the NX bit, and software dep, which I believe was something for the structured exception handlers.
So that's right. So Microsoft did sort of offer two things, hardware dep and software dep. And hardware dep is the real deal, where they're making sure that the page tables are checked before EIP goes to them to make sure they're real. And then I think before hardware dep they offered, I'm just not exactly sure about the timeline, I think it was before hardware dep was out, they offered what's called software dep. And software dep is not related to dep at all. So it's like a marketing ploy. Software dep was basically the safe exception handler stuff that I was showing you yesterday, where you can't just make the exception handler point to any old thing. It has to point to can't point at the stack, has to point to something not marked as safe SEH and so forth. And that's what they were calling software dep, even though it has really nothing to do
No, but
with,
if that was the case, I mean, I think you're correct that it was, I was just Googling it, and it does say that it was safe SEH, but we had booted our VMs into no dep mode, right? So opt in, and we didn't believe that our thing was opting in. So why wouldn't so my first exploit on that one used the just Oh, right, never mind. I used jump ESP, but the ESP wasn't in the right spot. So yeah, basically we wouldn't have been having the actual. Yeah, so I guess that's the question. Why couldn't we originally just point the function pointer wherever we wanted, like back to the stack, if safe SEH wasn't enabled?
Because in SP, right, so in Service Pack 2, Windows XP and beyond, by default, whether this kind of software depthing is enabled, so by default, when the exception handler code is going and parsing this linked list of exception handlers, it's just by default saying, all right, this points to the stack, no good. Even if you were to say dep equals opt-out or whatever, this sort of functionality is always turned on in Service Pack 2 and beyond. Now, in the unpatched virtual machine that I gave you, you can point the exception handler just right back at the stack, and it will allow it. And that's because back then, when Windows XP was just coming out, they didn't have this software dep and those kind of protections at all.
So this software dep is something that's compiled directly into the libraries. It's not like something that the OS is enforcing. It's something that's...
So safe SEH is something that is compiled into the DLLs where it says this is compatible with DLL with safe SEH or this is not compatible with safe SEH. And the exception handler code that's sort of parsing that linked list is looking at a couple things. One, it's applying these safe SEH heuristics, like does this DLL, is it compatible with safe SEH or is it not? And if it's not, just allow anything that's pointing into its address space. But also on top of those, it has like a built into it generic functionality. This points to the stack that is always not allowed.
Is that part of the OS or part of the libraries?
The libraries just say that they are compatible or not compatible with
So there's
safe
not
SEH.
actually any code in the libraries to enforce this. This is all enforced by the OS based on whether or not the library
Right.
says
It's
it.
enforced by the OS based on what the DLL is saying. But no matter what the DLL is saying, you cannot return straight to the stack. That's just like a rule that's built in there. But like I said, on the unpatched XP machines, all this stuff was sort of added to Windows XP later on after it was so widely abused by exploit developers. So in XP SP0, all this stuff was fair game. You could override the exception handler and point it wherever you want to, right back at the stack. And I think you'll also see that EBX points like directly at your exception handler or type of control data. So if there's unpatched XP1, if you override the exception handler in one of those bugs we find, you could just do like a jump EBX or call EBX instead of the pop-pop return if you wanted to. The pop-pop return still works. Okay, does that clear up the confusion there about what the software depth and the hardware depth was?
Yep, basically you're saying that the boot.ini doesn't control software dep at all in as XP post Service Pack 2.
Service Pack 2, that's right, just by default. Okay, so now it's time to talk about ASLR. We're not going to have to deal with this directly in this class because Windows XP doesn't have ASLR, but I will try to describe in detail modifier payloads to also bypass ASLR. It's actually, it's not really something that's going to give us too much grief. It just makes our payload a little bit more complicated. So as you should all know, in ASLR, you're basically just moving stuff around dynamically each time the process is loaded so that you can't know where the stack is located, so you don't know where your shellcode is going to be. And you also don't know where certain system functions are located and so forth. The base address of kernel32.dll is going to be randomized and so forth. But there are a lot of problems with this. Mainly, stuff isn't really that random, and you can also figure out where things are by information links and so forth. But I'll talk more about that a little bit later. So like in this case, I had this simple dumb code that I ran on my Windows 7 laptop here, 64-bit, and I just made it print out what the address of this function was. You can see that each time it's different. but also notice that the least significant bytes are still the same as 184. And that's because the ASLR in Windows isn't randomizing the locations of functions and so forth. They're really just randomizing the initial base address of the module. So they randomize where this binary gets put into memory, but then all the offsets in between are still the same. Does that make sense what I'm trying to say? It's just the base address that's randomized. It's not actually going in and making function down here and main up here now and that kind of stuff, because that would be very costly. Right? It's not too expensive of an operation just to change the base address and provide some relocations. But if you were to actually try to randomize everything, like the addresses of the functions and the actual DLL relative to each other, you would have to relocate a whole lot of stuff. And every time you launched it, this would have to happen every time you started an application in Windows 7. And it would obviously take a lot of CPU cycles just to accomplish that. But another thing worth mentioning is there's really not a whole lot of entropy here. And if we're talking about like a local exploit where we can try something hundreds and hundreds of times, then we can probably just guess, because we're just having to guess these top significant bytes. And it's pretty tractable just to guess this. If this is a remote exploitation scenario, we probably couldn't apply that strategy because the first time we're wrong, we're just going to crash the server, and then we won't be able to try again. And here's Windows XP. Thankfully for us, everything is always at the same address. Okay, so safe SEH, or hardware dev, or software dev, basically, is what I guess Microsoft was calling it back in the day to try to make more money. With safe SEH, I mentioned this yesterday. When you this is like on a per process basis, again, kind of like with GS, you have to tell the compiler, I want this thing to be compatible with safe SEH. And when you compile something with safe SEH, you basically register in your module what is considered a legitimate exception handler. And so when it's compiled in your binary file on the disk, it's going to have a table that says these are the list of valid relative virtual addresses where my exception handler can be pointing. And then when an exception happens, if the exception handler is pointing into that process address space of this safe SEH module, it's going to say, okay, I know this module opts into safe SEH. Let's see if the exception handler function pointer is pointing at one of those valid exception handler pointers. And if it's not allowed. Game over. But if the module does not opt into safe SEH, and again, most application DLLs do not, then you can point the exception handler function pointer anywhere in that DLL's or module's address space, and it will be allowed by the Windows exception handler code. So with the SEH overflow yesterday, I had turned off safe SEH in the binary, so we could return to a pop-pop return in the safe SEH overflow X section, address 4.1, blah, 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 whatever it was. But if this had been turned on, we could not have used that pop-pop return. We would have had to use a pop-pop return from Flash, because I hacked Flash to be loaded into that binary, because Flash doesn't opt into any of these exploit mitigations. So the important point there is, even though our main binary, this SEH overflow binary, the main process code opts into safe SEH, Flash does not. And so if the exception handler function pointer is pointing into Flash's address space, wherever it's pointing in there, it's going to be totally allowed, even though the main binary code opts into safe SEH. Okay, so you guys will see this up close and personal later, so I'll make you do it now. Like in this case, I'm in a debugger. This is another useful WinDebug command I didn't show you yesterday, by the way. I'm on slide 132 for you VBcast people. The ed command just allows you to arbitrarily change memory in WinDebug. So in this case, I've just arbitrarily hacked the exception handler to point to my prize function right before an exception is about to occur. So if save SCH is off, it will execute prize. But when I turn save SCH on, prize will not execute. And that's because I haven't declared in the binary that prize is a legitimate exception handler. So there's it without save SCH. And then with it on, it's never going to actually say, all right, this exception handler isn't valid because my binary option is safe SCH. And the exception handler is pointing at my binary, and where it's pointing is not registered as a valid exception handler, so I'm just not going to use it. Okay. So those are sort of the main things that we're going to have to deal with. A couple things that I didn't bring up in the slides. So some of the things that Visual Studio does as a compiler to try to make us more secure is it will, we already know it can do like this GS protection and so forth. There's still a couple other weird tricks that you might see when you're looking at an application. Normally, if you declare something like integer I pointer ATR char buff something like this, our stack would, it would just kind of like one-for-one translation. This is first on the stack, that's second on the stack, that's third on the stack. So we would have something like, this is I, this is PTR, stack scrolling down. This is buff, saved, EBP, return, and then what's above the return address? Does anyone know? The arguments to the function. So like R1. So this is like a typical stack frame. But Visual Studio in the later versions, I'm not sure if 2008 does this, 2010 definitely does. It will reorder the variables to try to make them like more secure, I guess. So what Visual Studio 2010 would do is it'd say, guess what? If buff gets overflowed, it could corrupt pointer and I without ever screwing up the stack canary, because that GS stack canary would be like right here. Again, GS protection turned on, because we would only corrupt up to here, so the stack would be left intact. So that's bad, because the attacker might be able to gain control of the IP just by corrupting these. So what I'll do, since I'm a smart compiler, is I'm going to reorder these and make it so that buff is pointing up here. And so our stack frame would end up looking like this. That way, with a typical Stack Overflow, you can't corrupt local variables. Because oftentimes, even just with corrupting the local variables, you can get control of the IP. And there's another thing you see it do sometimes, which is a little bit weird, and that's that it will create a copy of the command line arguments, like way down here at the bottom of the stack frame. And it will use references to this copied version. It's like the shadow version, I think is what they call it, instead of the arguments that are up here that were actually pushed before the call. And that's because a lot of times you can also get control of EIP by smashing all of this and then overriding the arguments, and then depending on how the arguments are used, you can control the IP that way, and that would happen before GS protection comes along and detects like a stack has been clobbered. So in this way, if the arguments are actually stored down here and this is what you're using, buff is up here, so there's no way you could corrupt these with an overflowing buff. So it's sort of variable reordering. It's not just an optimization. They're actually trying to apply some security heuristics and move things around so that potentially overflowable buffers can't override things like arguments and other local variables and so forth. But there's no real generic bypass for that, or because it's really just an inconvenience more than anything. It just sort of takes some of our targets away that we might be able to abuse. All right, you guys have any questions about those mitigations I just covered?